out the other side of a 3-meter source into a beam stop.
Thank you.
Thank you. So first of all, let me thank the organizers for this wonderful opportunity. Here and there, I will probably have some small overlaps with previous talks in this workshop, so I'm sorry for that. Okay, so the first slide, well, I think we by now all know very well that QCD admits a p-violation by the topological term, so we can, couple the topological charge via the term. And of course, we know that, we all know, well, we have seen presentation of the results during this workshop, so we now know that, this result constraint theta to be either vanishing or unnaturally small. And theta equal to 0 is actually the only genuine value for which the p symmetry is conserved. Actually, there will be also theta equal pi, but there is plenty of evidence that there is spontaneous symmetry breaking for that value. So this fine-tuning issue is not a strong CP problem. So yeah, by now we have seen, several possible solutions to this problem. Also within QCD, well, of course, we know very well that if we have a massless quark, we could rotate away the theta term by an appropriate U1A global axial flavor transformation. But of course, we know that the up quark, which is the lattice quark that we have, as a non-zero mass from lattice simulations and also from experiments, so that's been ruled out by now. Well, we also see other possible dynamical simulations within QCD, but of course, I'm here to, describe a beyond standard model solution of the strong CP problem, which is the Peccei-Quinn axion. So I want to review a little bit some details about the model, and then I will link it to the study of QCD topology. So we know that we have, to supplement the standard model with a few new ingredients in order to, introduce the axion. So first of all, we need to introduce a new global axial abelian symmetry, which is the U1 of Peccei-Quinn. And we have to assume that the symmetry is spontaneously broken at a scale which is of the order of FA, which is the axion scale. Well, we have this very loose constraint coming from cosmological and astrophysical bounds. So we expect very loosely to have FA in this range. Of course, our goal is to constrain it more via QCD. I will show how. So the simple recipe provides a dynamical mechanism, which is called the PQ mechanism, the Peccei-Quinn mechanism, to solve the strong CP problem, because of course the spontaneous breaking of the symmetry gives us a new pseudo-Nambu-Wilson boson, which is the Peccei-Quinn axion. Okay, so we have this particle in the spectrum now. And by anomaly matching, because of course the symmetry is axial, so it is anomalous under the gauge group of QCD. So this binominally matching effectively generates at very low energy scales a term which couples the axion field to the topological charge density, which is Q of X. Of course, this is very important because this is actually independent of the particular UV completion that you are considering for the axion. For instance, in the talk by Laura Covey, we've seen some of them, but that's fairly, independent of the particular model that you want to consider to, explain the axion also at the UV level. And besides, since the axion is a Nambu-Wilson boson, of course, it possesses a shift symmetry, so we are able to essentially shift the vacuum expectation value of the axion field. Is there a question online?
Okay, guys, please check who you're sending the message. So please check your chat on Zoom. Thanks.
Sorry. Okay. So, well, I was mentioning that we can essentially shift the vacuum expectation value of the axion field by applying a U1 Peccei-Quinn symmetry. Okay, that's a general properties of Nambu-Wilson boson. So essentially, we can relax theta to 0 by an appropriate shift, okay, of this axion field. The bonus that we got with this recipe here is that now the axion coupling to standard model particle is suppressed as this large scale FA. So it is also possible to consider this hypothetical particle as a possible dark matter candidate, and so it may play an important role in cosmology. And that's exactly what I want to talk about now. So essentially, if we want to understand the role of axion in cosmology, we have to consider the axion field evolution in the Friedmann-Lemaitre-Robertson-Walker metric. This is, I mean, a generic equation for a scalar field in this metric. And here we have the axion potential, the effective potential. Actually, it's a derivative. Well, for now on, I'm just considering for this sketch, just the leading order term, which is just the mass term, okay? While h is the Hubble rate, so it's the ratio of r dot over r, where r is the scale factor of the universe in the FL-RW metric. So if we define the temperature T's, which is essentially defined implicitly by this relation here, because so far I haven't talked about the temperature dependence of the axion mass. Okay, we can essentially consider three moments essentially. So for early times of the universe evolution, so closer to the Big Bang, essentially this term here dominates over the mass term. Okay, so this is like a friction term, which essentially freezes the evolution of the axion, which is essentially, still. Of course, theta can assume any non-zero value. Of course, we can argue if we are pre or post-inflation, but that's more a matter of cosmologists. Then when we reach a temperature which is about of the order of T's, well, the axion starts to feel its potential. So starts to descend towards the minimum, which is instead theta equal to 0, as I will discuss in a moment. And then it starts to oscillate when the temperature becomes smaller than T's. And we know that, of course, in that case, theta, of course, is dynamically put to 0. And then we have decaying oscillations of the axion field. And the number of particles that have been produced during the descent and are then fixed during the oscillation. So essentially, what we want to do is to solve the axion equation to find the time evolution of the Hubble rate, and then to solve the axion equation in order to find the axion energy density, the relic one, for very large times of the universe evolution, so nowadays. And then we want to compare it with the observed dark matter energy density, essentially, because this can account for whole or a part of the observed dark matter energy density. So essentially, we need to provide information about the axion effective potential. So we need to plug this into the game in order to compute omega A, which is the axion energy density, which is of course a function of Fa. So once we solve these equations and we have omega A as a function of Fa, essentially we can put upper bounds by comparing omega A with the omega dark matter. So that's essentially what we, the so-called misalignment mechanism. So talking about the axion effective potential, of course, I now come to the main point of my talk, which is, of course, the study of the theta dependence of the QCD free energy density, which here I define in terms of the logarithm of the partition function, where a non-zero theta term is turned on. This is, of course, written in the Euclidean, and I've integrated out fermions. Actually, the thing is pretty simple. So essentially, when we shift the axion field so that we kill the theta term, well, we end up with a sort of effective, theta term. Well, theta is replaced by A over Fa, okay, because this is what remains coupled to the topological charge density. So if we integrate out QCD, of course, we simply find that the effective potential of the axion is just the same functional dependence of FQCD as a function of theta, but where theta is replaced by A over Fa. Okay, so if we know the theta dependence of the QCD free energy density, we also know the dependence of the axion effective potential as a function of the axion field. So of course, this means that to constrain axion physics, we need the QCD input of the theta dependence of the free energy density. So this is just, a sketch to summarize what I've told you so far, okay? It is taken, actually adapted from this very nice work. I think this is a very clear picture of, what I told you so far. So essentially, the green line here is essentially the axion field divided by Fa, which is called here theta A. So essentially, as you can see, if the temperature is much larger than T's, then essentially there is no evolution of the axion field. Then at a certain point, the axion field starts descending, and then it starts oscillating with the king oscillation around 0, which is of course the real the real minimum, okay, the real vacuum. And conversely, if we look at the number of axions, so we essentially assume that there were no axions at the Big Bang. Of course, this number stays 0 until the axion field is frozen, and then of course it starts growing, and then it starts of course having decaying oscillation around a relic value, which in principle should be possible to be measured today. Okay. So now I'm going to dig into the theta dependence of the QCD free energy density, okay? So, well, essentially what we usually do, this has been already, described also by Massimo Delia in the first day. Well, usually, essentially, we perform a Taylor expansion of this quantity here around θ equal to 0, which of course assumes that this quantity is analytic in θ equal to 0. And we define these coefficients here, Chi, B2, and B4, which essentially parameterize a Taylor expansion around θ equal to 0 of this free energy. And of course, if we do the same expansion of the effective axion potential in the axion field, of course, it is very easy to match which coefficient is which. Of course, this quadratic term here, which is of course the topological susceptibility, so the mean value of Q squared divided by the volume, it is related to the axion mass. And then we have also higher order corrections. For instance, I will also talking about B2 in the following, which is instead related to the fourth cumulant of the topological charge distribution at θ equal to 0. So it's an higher order cumulant, okay? So usually we want to compute these quantities here, Chi, B2, and B4, and so on, because in this way we have access also to the effective axion potential. Before going to the lattice, because I'm lattice theorist, I also want to review some known result from analytic computations. So, well, we have already heard about Carnot effective Lagrangian, so we know that it is an effective Lagrangian with the non-Bosol's bosons as degrees of freedom. A possible way to study theta dependence in this case is to trade the theta term for a phase in the mass matrix. Of course, it is possible. In the full theory via, as I already said, via a new 1A transformation, because the anomaly shifts theta, and also we get a phase here in the Planck mass. So essentially, if we mimic what happens in the full theory in the Carnot Lagrangian, we end up with a phase here, which is proportional to theta. Then the free energy is simply obtained from the Carnot effective Lagrangian. Essentially, we look for a vacuum configuration, so which has no dependence on the space-time coordinates. And essentially, we minimize the Carnot Lagrangian, which accounts to minimizing the potential, because of course this term is 0 for a configuration that doesn't depend on the space-time coordinates. And then we compute the theta dependence of the free energy like this. And for two quark flavors at leading order, it is possible to obtain a very compact and nice expression, which only depends on m pi, f pi, and on the quark masses. And of course, from this, it is possible to compute the topological susceptibility. Yes.
I think that's allowing no comment at this point. I think we have assumed that the determinant of U, that the argument of determinant set 0 in order to derive the last equation. They cannot just a comment that also relates to what I said in after Ulf Meissner's talk yesterday. To derive this last relation, there I think one has to know the with the square root. That's when one assumes that the determinant of the argument of the determinant of U is 0 after you have moved the phase into the quark mass. Yeah. And that is where we basically deviate. I just wanted to clarify this one more time, and then move on.
Yeah, yesterday we saw probably a more complete derivation of this equation. Here I'm just reviewing the main results, of course. So yeah, once that we have this expression, we can of course compute the derivatives, and we can end up with these simple expressions, for instance, for Chi and for B2, which only depend on the F pi and pi and on the ratio among the U and D quark masses. Of course, this is an F equals to computational leading order. But actually, we also know next to leading order term contributions for two flavors. So these are essentially the two important results that have been computed in this work here for two degenerate flavors or two physical core masses. And just as a comparison, of course, we can compare with the full with the French theory result, which was, reviewed by Massimo in his talk. Of course, this is much larger because, of course, the contribution of light flavors is to suppress topology. We know it. Actually, we see here that, of course, in the kernel limit, this quantity here goes to 0 because, of course, we know that in that limit, as I already said, we can absorb theta dependence. Okay. As for B2, these are the results, and here there is a little bit, strange fact that that is very evident is that in the pure Young-Mills case, we find that B2 is actually very close. It's compatible actually with the value that we get in full QCD with physical quarks, but I do not have comment on this. I think it's just a coincidence because I don't think that there is a first principles argument to to explain why they are so close. But these are the results from the this is a lattice result, and these are the results from color perturbation theory. Okay.
That is for n equals 3.
This here.
Yeah, Young-Mills one.
Young-Mills.
Yeah.
No,
SU1, SU3.
No, SU3. Yeah, sorry, this is SU3. Yes. Okay, so these are of course zero temperature results. Actually, we can also provide finite temperature results for within the kernel perturbation theory formulation, but of course we expect this result to hold below the crossover because above the crossover the kernel condensate is 0. So instead, if you want to provide some analytic prediction for the behavior above the crossover, and in particular for asymptotically large temperature, then we have to rely on the so-called dilute central gas approximation, or DIGA for short. So here I just want to, these are of course very well-known results, but I would like to stress 2 points, which one point actually, which is I think very important. So the dilute central gas approximation relies actually on 2 different assumptions. One is the semi-classical approximation, which means that you essentially assume that your gas is dilute, so you can treat your instantons as indistinguishable particles. And then you have also perturbation theory, meaning that you perturb, you have Gaussian fluctuations around one instanton configuration that you integrate in the path integral. Okay. So actually, it is possible to derive this expression here just from the diluteness assumption. Okay, so essentially the diluteness assumption completely fixes the non-quadratic dependence of the free energy density, which is the cosine, the very famous cosine of theta here, and fixes the general form of the topological susceptibility, which is just dependent on Z1. Which is the one instanton partition function, and the only dependence on the temperature is contained here. So there is no dependence in the B2 and B4 and so on terms. Okay, and of course, if we match this expression here with the Taylor expansion I showed you before, we find, for instance, the very famous DIGA prediction for B2, which is -1/12. Okay. Instead, if we want to know more about the temperature dependence of the topological susceptibility, we also need to, perform a perturbative computation around the one instanton configuration. And the very famous result from, Gross and collaborators is that the topological susceptibility is suppressed as a power law of the temperature. And we know the exponent as a function of the number of flavors and of the colors. And for instance, for pre-light flavors, which is relevant for lattice computations, the exponent is predicted to be 8, around 8, close to 8. So of course, this prediction has been routinely applied in axion computation because it's very simple, and it is expected to hold for a high temperature, so very close to the Big Bang. But the problem is that if you take a look at the picture I showed you before, we actually have to know what happens also at the GeV scales, which is not so far from the crossover, okay, which is of the order of 100 MeV. So of course, it is very unlikely that we can rely on the DIGA, down to those temperatures, okay? So this is why it has been proposed that, we gain full control over the temperature dependence of the topological susceptibility from lattice simulations. And this is what I want to talk about now. So, sorry? Well, in Canal perturbation theory, well, I think you can arrive close to the crossover from below, but yeah, you cannot trust. I know there are some papers where they try to constrain what happens above the crossover from Canal perturbation theory, but I don't know if they are reliable. I don't think so, because the Canal condensate is 0. So. I will arrive on that. Yeah. Essentially, if you want to compute the topological susceptibility on the lattice, you have to face several non-trivial computational problems. And my aim in this talk is to, review them, to, describe them, and to review also some strategies that have been applied, okay, on the lattice. So the first problem that is very, it is clear from what I said just now, is that, of course, the topological susceptibility is computed from the mean value of Q squared, so from the variance of the topological charge distribution. So what you want to have is to have a nice, this is the time evolution of the topological charge during Monte Carlo simulation. So you want to have a nice oscillating history that explores several topological sectors, because you want to compute this quantity here, okay? This Q squared here in order to derive the topological susceptibility. But at high temperatures, essentially chi is suppressed. So this product here is much more than 1. So it is typically of the order of 10 to the minus 1, 10 to the minus 2, or even smaller if you go to very high temperatures. So what happens is that essentially you end up in this situation here, where essentially you observe a story which is essentially 0, and sometimes you fluctuate in the Q equals 1 or minus 1 sector, but such fluctuations occur very rarely. And this problem is exactly due to this suppression here, because of course, with this condition here, the Q equals 0 sector is largely dominant, okay? So these are two examples with the same lattice spacing, but for 2 different lattices and for 2 different temperatures. And you can see that the difference is dramatic, okay?
So this is not an algorithmic issue, this is physics.
Yeah, exactly. This is not, I will talk about that in a moment. This is not critical slowing down. This is just physical issue due to the fact that the volume is small. If I could afford much larger volumes, then this problem, wouldn't be there, okay? So, I think it is pretty clear why it is a problem, but I also want to make this picture because I think it makes it more clear. So essentially, if you suppose that, the dominant sector is a 0 sector, and then you have a subleading sector, which is the Q equal 1 sector, okay? And all the other sectors can be neglected. You can approximate the topological susceptibility as essentially the ratio between pi1 and pi0, which are the probability of visiting the 1 and 0 topological charge sectors. So of course, this means that measuring on the lattice the topological susceptibility essentially means to count how many times your Monte Carlo history visits the Q equal 1 sector, okay? Of course, we know that, if we approximate this as a binomial, of course, we know that the relative error we are having on this quantity here is proportional to the square root of the number of countings, okay? So of course, if the number of countings is suppressed and goes to 0 because of this condition, of course, you're gonna have, an error which blows up, of course, on this quantity, okay? So another serious issue, oh, sorry, but you cannot see the title, so maybe I should hide this. Okay. Okay. Okay, so another problem is essentially related to the realization of the chiral symmetry on the lattice. This is the partition function, and of course we know very well the determinant of the Dirac operator is a weight for the configuration that enter in the path integral. So of course, if we write like this, the determinant, of course, we see that the role of the quark mass is to suppress configurations in the path integral if the mass is light, and if we have 0 modes. which of course occurs when we have we compute the Dirac operator in the background of a gluon configuration that has a non-zero topological charge because of the index theorem, essentially. So at least this is what happens on the typical configuration that we have on the lattice. Okay. The typical visualization that we have in finite temperature simulations do not preserve the chiral symmetry on the lattice. So for instance, Wilson fermions or Segre fermions. So we don't have zero modes because we cannot have chiral modes for the, eigen modes for the Dirac operator. So essentially, since there is a shift in these minimum eigenvalues that we observe in the Dirac operator, this suppression here that should occur in the continuum is much less efficient on the lattice. So essentially, this means that you have huge cutoff effects for topological susceptibility at finite temperature. And this is an example for a temperature of the order of 430 MeV. This is kind of the 1/4, and as you can see, by halving the value of the lattice spacing, you observe that the value of the topological susceptibility changes by, more than 1 order of magnitude in this case. So of course, since we have a very huge, corrections, of course, it is very difficult to have full control over the continuum extrapolation. For instance, in this case, it is essentially compatible with zero within the error. So a strategy to reduce such large lattice artifacts would be needed. And finally, I come to the question of Andrea. So there is a further problem, which is a topological critical slowing down, which is essentially an algorithmic problem, which is of course very well known. It is related to the fact that when we approach the continuum limit, of course, the standard algorithms become less and less ergodic. And this is, for instance, an example at zero temperature. As you can see, as we decrease lattice spacing, of course, we see less and less oscillation, and eventually we see no oscillation at all. Of course, this is an algorithmic problem, which is essentially related to the fact that in the continuum, topological sectors are essentially separated by infinite free energy barriers, so essentially by configuration with infinite energy. Okay, so of course, in this case, better algorithms would be needed to, overcome this problem here. So now I want to review some strategies that have been proposed and applied. For instance, I want to start from the strategies applied by the BMW collaboration in the Nature paper. So essentially, their computation relies mainly on these two strategies. So the reweighting strategy is essentially what they do to suppress these large lattice artifacts that they have for the topological susceptibility. Essentially, they modified the distribution of the path integral by hand a posteriori on their configurations by adding by hand this weight here, the W of Q, which essentially, as you can see, restores the suppression with the quark mass that you expect to have in the continuum path integral due to the determinant of the Dirac operator. While this lambda here is essentially the would-be zero modes that you have on the lattice due to the breaking of the chiral symmetry. So their argument is that this quantity here tends to 1 in the continuum limit, and so they expect that they recover the proper continuum limits.
Is the local operation in terms of relation function?
No. It is not. They only have a small comment on the paper that says, well, but also routing is not local, but routing is fine, so also this is fine. Summarizing. The other strategy, which essentially they use it to overcome the problems of the dominance of the Q equals 0 sector and also the critical slowing down, if you want, is essentially to use the so-called fixed sector integral. So essentially, they assume the Daiga in order to write the topological susceptibility as this ratio here of pi1 over pi0. So essentially, they reduce the computation of chi to the computation of this ratio, pi1 over pi0. And the idea is that, well, they compute it for a temperature T0, a reference temperature where they observe some fluctuations of the topological charge. and then they, derive it for a temperature T for which no fluctuation at all is observed in the Monte Carlo history by this interval here, where this quantity here B1, sorry, is defined essentially as the logarithmic derivative with respect to the temperature of this ratio here, which essentially they write as a difference between the expectation values of the gluon action in the 1 and 0 sectors, which can be measured also in simulations where you observe no fluctuation of the topological charge, because of course you will still observe fluctuations of the action, okay, of the gluon action. Okay, this is just a sketch of their strategy, but I mean these are the main points they rely on. Okay.
So this one is just an RGB type of programming, or what is it?
Yeah, I guess that you can. I mean, I guess that you can do it like that. Yeah. Yeah. But the main point is that, I mean, in some sense, they hide. The DIA result. Which is something they should verify, not assume. But that's my personal opinion. So. Okay. Now I will also talk about some of my, of the strategies that I've pursued. So this is one of them. So essentially, this is kind of opposite to what they do, because essentially, the idea is that I modify the path integral distribution by adding a potential that enhances the probability of visiting topological sectors which would be suppressed by summing a topological potential, which at the practical level is done like this, okay, in order to improve the number of times you visit the topological sectors between minus Qmax and Qmax. But then I essentially take this potential away by a reweighting, which essentially brings you back to the original distribution. Okay, so this is a more standard reweighting, let's say. Okay, it's different from the BMW one, of course. And this, and here you can, you can observe the results. So with no potential, well, this is essentially the same story of the topological chart I showed you before. This is what I would observe. While with the multi-canonic algorithm, it is possible to, have to observe lots of fluctuations, and also to observe higher charge sectors. Okay, so it is possible to improve the measure of the topological accessibility, of course, in this case, because you observe lots of fluctuations, so you improve the number of you improve the countings. Okay, according to the argument I explained you before.
Can I ask you what math is actually using before and here? This is QCD.
Yeah. We use for the fermion sectors rooted stout improved staggered fermions. Of course, this just, not of course, but in our case, this just regards the gluon fields, because the topological charge that we define in the action is just the gluon one. So, and we also have, of course, the gluon action, which is that two-level semantic improved gluon action. So, yeah.
Why that choice of the shape of the potential?
Well, the choice of the shape of the potential is not critical. Because of course you can choose it how you like it, because in the end it doesn't matter, because you're weighted. So of course, so. Yeah. No, this is just a practical choice that we found by trying different ansatses, and well, essentially the idea was to have like a linear, a linear shape here, but then we didn't want to have like a sharp peak here, so just we choose a sort of a relativistic potential form. But this doesn't really matter. The important thing is that you you don't alter too much the distribution, because of course you want to visit configurations that are still relevant also in the original path integral, because otherwise you are sampling irrelevant configurations if you have a potential that brings you too much far away from the original distribution. Okay, so when you satisfy that condition, the choice of the shape of the potential really doesn't matter. This is just an example. Okay. Okay, and then as for the problem of the large lattice artifacts affecting the topological susceptibility, as I already said, I mean, the typical standard discretization that we have is the gluonic one, which is just, I mean, a straightforward discretization of the GG dual, I mean, expression that we have. This is a very simple naive one in terms of the plaquette, which is just, I mean, the standard loop. Of course, we can have improved discretizations, but I mean, the problem is that this kind of discretization here, the gluonic ones, know nothing of the chiral properties of the fermions, which are, of course, I mean, of fundamental importance, of course, to define the topological susceptibility. So a possible way to overcome this problem is to adopt what we call fermionic definitions of the topological charge, which means that they are justified, I mean, they are discretized version of the index theorem, okay? Well, actually, well, this is an example from the work here, where they compared the continuum scaling of the topological susceptibility at 0 temperature with the twisted mass Wilson fermions. This is the standard Warwick computation, while this is the fermionic computation with spectral projectors, which I will explain in the next slide. And as you can see, the lattice artifacts are much more milder. Of course, this allows to have a much better control on the continuum extrapolation because the error bars in the end are much smaller. Okay. So I would like to discuss a couple of types of fermionic discretization. But first of all, let me just remember these very well-known properties of the Dirac operator. So we know that the index theorem can be rewritten as Q equals trace of gamma 5, meaning that if you compute this trace on a base of eigenvectors of the Dirac operator, u lambda, well, of course, this ends up in this same expression, so that the counting of zero modes, because we know that the slash is entire Hermitian, but is also gamma 5 Hermitian. So for each u lambda, we have a twin with the complex conjugate eigenvalue, which is gamma 5 times u lambda. So we end up with this relation here, which is essentially 0 or 1. I mean, if the mode is a zero mode or not. Okay. So this is all very well known. So I'm sorry if I say trivial things, but I mean, I need them to define these observables here. So one possible definition, which has been explored in several works, for instance, the work by Prest and Sharma, also by Maria Paula and collaborators, is the one that relies on the chiral susceptibility. So in the continuum, this will be like this, because essentially, if you compute this trace again on this basis here of u lambda, essentially you end up with the trace of gamma 5 times m to the minus 1, which just cancels out with the m in front. Okay, so this is just exactly the index theorem, a way of writing the index theorem. And so from this charge expression of the charge here, you compute the topological susceptibility, you find that it is equal, apart from a factor of m squared, to the so-called gamma 5 disconnected chiral susceptibility, which is exactly this expression here, which is, however, very difficult to compute on the lattice. So this is why usually it is assumed that the U1A symmetry is restored, which should be well verified sufficiently above the crossover, so that we can make this equality here, which of course holds only if the U1A symmetry is restored. And so we end up with just a simple disconnected chiral susceptibility, which is written here, which is more amenable to be measured on the lattice. So another possible feminization, which is actually the one that I have employed in my computations, is the spectral projectors one, which is instead relies on the expression of the topological charge as the sum of the chiralities of zero modes. So essentially what we do on the lattice when we do not have exact zero modes, essentially we take this expression here and we just extend the sum, which in the continuum would be only over zero modes, up to a certain threshold mass m, capital M here, and we sum the chiralities. And this is called spectral projectors because, of course, you can read from here. I mean, you can translate the expression here as a trace of gamma 5 times PM, where PM is essentially the spectral projector over the eigenspace of the Dirac operator, which is spanned by this eigenvector here with the eigenvalue smaller than m. Actually, this definition here, when we use this charge here to compute the susceptibility, needs a renormalization, which is just multiplicative one. And the nice thing is that also this renormalization constant can be written as a ratio of traces of these spectral projectors here. Actually, on the numerator, we can write just the nu of m, which is just the number of modes that you find below this threshold here, this cutoff here that you choose m.
Is the gamma bar missing, or is it a trick I don't understand?
Sorry, where?
And the expression for the disconnected susceptibility.
Here?
Yeah, the gamma 5 missing inside the correlator, or is it a trick I don't understand?
No, the trick is that here you assume that U1As are stored, so that you can go from the gamma 5 disconnected susceptibility to the one without the gamma 5. So that's exactly the point. Of course, this holds only if U1A is restored, because I mean you can map the one with the gamma 5 with the ordinary disconnected one. Otherwise, of course, if the U1A symmetry is broken, they are not gonna be equal. So yeah, so that I mean the real thing is the one here with the gamma 5, of course. That's a trick because it is very difficult to compute it on the lattice.
So when you use a spectral projector, you somehow go back to an eigenvector discrete expression of the previous formula. That's essentially.
Yeah, because well, at least in what I did was essentially to take the to take the our Dirac operator and to exactly compute the first certain eigenmodes and eigenvalues and compute these spectral sums here. So the pseudo-chiralities and the sum of pseudo-chiralities, yes. But of course, it is much more expensive as a computation. Okay, if there are more questions, I continue. Actually, I'm almost done. So this is a plot that should appear soon in a paper we are working on. There's also Andreas in the author list. So essentially, these are the new results that I have obtained using the spectral projectors and the multi-canonic algorithm. While these are the results of the BMW collaboration that use the weighting method that I explained you before. And then I also plotted here the result from Peccei, Sharma, collaborators that were obtained. Well, this darker band here were just obtained from harmonic computation, while this lighter band here was obtained from a fermionic computation using the Cara susceptibility that I showed you before. So these are all 2+1 results. My results and the BMW results have been continuum extrapolated temperature by temperature, and then we fitted the temperature dependence. While in this work here, they essentially performed a global fit where they, fit simultaneously the lattice spacing dependence and the temperature dependence. And also, they actually do not have results for the physical pion. So, just to be fair and to make this plot here, to make this comparison here, I essentially rescaled their results by mpi, which is actually a Daiga prediction, but just to be fair. Okay. So, essentially, we find that a very good agreement with the Daiga prediction, essentially, at least for the exponent, because the Daiga predicts that the susceptibility suppresses a power law, which is an exponent of 2, and actually these lines here are, they have a slope which is very close to 2. It is compatible with 2 within the errors. We can fairly say that at least for temperatures of the order of 300 MeV, we observe a very, a Daiga-like power law. Okay, this is a fairly, there is common agreement among the different, the different results that I'm showing that this is the case. But of course, as you can see, there is no good agreement among the prefactor of this parallel here, especially spectral projectors seems to point out, at least in this range here, which is between 300 and 400 MeV, they seem to point out, a much larger value of about, almost a factor of 10. So how much this affects the axion computation is not clear, probably not much. But nonetheless, this is if you want, a kind of an unrelated problem, because the problem of computing the susceptibility is interesting per se, apart from the axion. So I think that by now there is no clear common quantitative agreement on these results. So I think that this is should not be considered still as a fully closed chapter. Yes.
Displacement of the data, which is systematic, is there any understanding why there's not agree somehow?
That's exactly what we would like to understand. The fact that that different strategies lead to such different results. It's something that should be investigated, because, well, of course, the real difference among the two computations is that in one case, we essentially used just a Fermionic definition of the topological susceptibility to suppress the cutoff effects. While in this case here, well, they perform a reweighting, which is, their way of dealing with it. But I think that probably we should, understand why these two strategies here to reduce lattice artifacts lead to such different results, at least for the temperature which are closer to the crossover. Yeah.
I wonder if you have thought about using the overlap operator as a regulator to calculate the 0 moles. Very clean.
Well, no, that's an interesting question. We could do that. Well, actually, the point is that we have computed the spectrum of Segre operators for several purposes, because of course it is interesting to compute lots of observables, like for instance also the chiral condensate and so on. But of course that's a possibility. Of course, the computation, at least we try to to diagonalize the overlap operator on some of our configuration. And of course, it is a much more expensive computation. So of course, we need more, more computational power to perform such a full computation for for 5 temperature. We had like 4 or 5 lattice spacings for each temperature. We have between 500 and 1000 configurations for each point. So that would be very expensive. So of course, this is something that should be done, but to do that we need more computational power. So thank you for the suggestion. Surely it's something that should be done to compare the chiral properties of our spectral projectors definition with the with the overlap, of course.
The gradient flow will be cheaper. What gradient flow? Gradient flow?
You mean with the gluonic definition?
Yeah. No, not for that. Just look at the gauge. That has been done, I guess.
Yes, of course. I'm not showing here, but the problem with the gluonic, as I already said, is that it suffers from very huge cutoff effects. So it is very difficult to perform a controlled continuum extrapolation with the gluonic. That's exactly what we want to avoid. No.
They're saying that the gluon definition flow uses large cutoff effects, but they haven't tried it. So the product that topology susceptibility.
No, I don't have it, but yeah.
From the paper.
No, I do not have it on the slides.
Yeah, the continuum limit.
Okay, no, yeah. I have this one here. Yes, no, I do not have a comparison with the projectors.
The one with the spectral projector and the guy.
Yes, sorry, yeah.
Yeah, maybe you explain
Yeah. Yeah, so this is the computation, from the gradient flow with the gluonic definition, and this is the spectral projectors one with the twisted mass Wilson fermions. So that's why we want to avoid.
Could be, yes. It's. Have you played it with spectral flow? No. For instance, if you for a pion mass of, let's say, I remember that
let's say 350 MeV. I mean, if you compare the topological susceptibility extracted by spectral projectors and by gradient flow, you realize that 70% of the number you get, I mean, for the susceptibility extracted with gradient flow is not acceptable. It's like,
yeah,
I found it like.
We found exactly the same with Wilson Fernand. So the Bionic definition is parabolic, like that.
Yeah.
And then when we switch to the Bionic definition, then immediately that's the practical connection. But it is
When you say fermionic, which definition? Spectral projectors or
the chiral susceptibility.
Okay.
That was really very nice.
Yeah, with spectral projectors, we find that the ratio between the, I mean, if you compare the slopes, so which tells you, I mean, the magnitude of these artifacts, we observe that the ratio between the two slopes is like 2 orders of magnitude. So, I mean, it's like a factor of 100.
It is so natural because in the end, I don't know what you think, but the Bionic definition again is more local. So whenever you work with kernels, yourself.
Well, my impression is that, yeah, my impression is that the Gluonic definition knows nothing of the chiral properties of the fermions. While if you use a definition which is based on fermions, although they break the chiral symmetry, but the point is that exactly the same, I mean, low-lying eigenvalues that, I mean, that prevents you to have the proper suppression. Also, you use them to define the topological charge. So, I mean, it's like a sort of error compensation. Of course, it's a very naive idea, but
Well,
that's my understanding of the question, I mean, of the problem.
Already the two definitions are equivalent from the quantitative point of view. But this is just a question of chiral effects.
Yeah.
And,
Sure. No. Of course.
There is also a fermionic determinant, and so it's the coupling of the determinant with the Gluonic definition that gives you information about the zero.
Yeah, but I mean, it's non-trivial that changing. I mean, for the same distribution, it's non-trivial that you change your variables and you correct the error, no? And of course, yes, I have to mention that. Of course, there are ordered entities that guarantees that the continuum limit is exactly the same. Of course.
That's absolutely absolutely.
Yeah, well, first one was probably supposed many years ago. The thing is, the idea that using the source scale going back from the divergence you want anomaly. You make this through 2n times p.
Yeah.
On chart, and you integrate it over to mu for dimension together. But that can be subject to very large discretization errors when you don't have you don't really have that relation.
I use the restoration vector.
Yeah, the thing is that if you take Peter Hagenbach, it's just exact one relations with overlap fermions. It doesn't matter which you calculate this way or that way.
Yeah, but
so once you have a non-chiral fermions, then it's long.
Well, actually, I have to say that and so we are using Wilson fermion at maximum speed. So that's basically the best you can do without entering really expensive discretization. So this may be the reason why that is so bad under control. You're absolutely right. That's probably the name. And then of course we are
But I think that it was also checked that I mean how well the UNA is actually restored at high temperature. And I remember that they found that of course not soon after the transition, but very close to the transition. I mean above the transition it is. Yeah, exactly. Yeah, exactly. I remember that. I mean, at least in this temperature range here, it should be. But I mean, these are spectral projectors, so I mean, the chiral is this one here. But at least for the result of Sharma and Petrescu, they found a green result. So I mean, within the railroads, at least is a systematic that they do not observe. Okay. Then we can, of course, argue if it is correct to assume that, but okay. So, do you have a question also?
My question was more of if you have ever tried less local operators for
like the overlap?
No.
semantic.
including some larger packets.
Improved, yeah.
No.
They have any significant effect, or it's still, way worse than the change.
No, I mean, I have compared with the topological, I mean, with the warning susceptibility, just compared from the, I mean, the standard Clover.
Like, I mean, you could like,
Yeah.
Rectangular.
Windmill, windmill.
Yeah.
I mean, differences of the order of a to the power of 4, right?
We have some studies on a single gauge. We saw that converges to an integer in a better way.
Yeah.
But yeah, in terms of the susceptibility, we haven't done a systematic study.
But it is exactly the same as the theory.
Yes.
So it doesn't
No,
seem like
this is 11 improved there. So there is no recipe.
No, I understand that you can do it more formally, but conceptually, somehow either you use the operator or you use the base that's the same.
But I think what Andrea said is that, I mean, we use like semantic improved, I mean, with rectangular, I mean, this converges to an integer much faster.
No, I understand, but what
Closer
what I'm saying is that
Sorry.
if you don't improve the operator and you mirror more text, that's equivalent.
There is no smearing. It's just adding some rectangular pieces.
I understand, but you instead of adding.
So you compute the definition with no smearing.
It's flowed. It's flowed. So first you define the field tensor, including larger plaquettes in order to remove or the up to 8 to the 4 at the level of perturbation theory, and then you flow those gauge lengths.
Okay. And do you obtain different results from the?
At the level of the single gauge, yes, we see a better convergence to the integer value, which is usually related to the kind of effect of the susceptibility. But the systematic study of the susceptibility step itself we didn't do.
We have plots in the first paper on the NDM, I mean, the TMC. I think we have plots of different, basically smooth with Iwasaki, semantic, and Wilson, and we see that we get slightly different results.
Yeah. And so the gauge action is the same. I'm talking about the observable. Yeah.
Okay.
I'm talking about the observable.
Observable.
Sorry,
So
okay.
the field tensor that define the charge.
Are there more questions? Okay. No, I just want to, I mean, to show these results also for the B2. I mean, the diagram predicts that B2 is equal to -1/12 with no temperature dependence, but I mean, the result from the PISA group, I mean, they point out that there is a small deviation from the diagram if you go closer to the crossover. Although these results are finite lattice spacing results, so they are not extrapolated towards the continuum limit. So probably we should make a more I mean, complete study of the continuum extrapolation temperature by temperature. So this is a quite old result, but I wanted to show them anyway. Also because I think that it kind of fits what we find here. That I mean, okay, yes, we see the diagram, but I mean, for temperatures of the order of 300 MeV or larger, which I kind of agrees with they find here. So I think that overall the picture that emerges is that. I mean, as for the non-quadratic part of the theta dependence, and as for the exponent of the temperature dependence of the susceptibility, it is probably fair to use the Daiga for temperatures in this range here. While for the, I mean, for the prefactor, it is surely not wise to use the Daiga prediction because, I mean, already BMW results pointed out that the Daiga result underestimates the prefactor of the susceptibility by an order of magnitude. Our results are even larger. So, I mean, coming back to your question, it's surely not. I mean, you should not use Daiga even up to, I mean, to the GeV scale. Of course, this is 600 MeV at most, but I mean. Okay, we observe a significant deviation as for the prefactor, not for the exponent of probably 2, but okay. So probably, I mean, as I already said, there are 2 assumptions mainly that I mean underlie Daiga. So probably it is fair to treat instantons, I mean, independently for this temperature, but for sure the perturbative result around one instanton is not so reliable, probably. So yeah, well, I think that essentially I've already, summarized the main take-home messages I would like you to bring home after this talk. And just to have a brief future outlook. Well, I think that currently, I showed you different strategies to deal with the problem of the dominance of the Q=0 sector and also of the problem of large cutoff effects. But I think that the topological period slowing down is still, a very difficult, problem that has to be still satisfactory, faced. And this is very important because we need to face this problem both if we want to go to finite spacings to refine, for instance, our result, which of course it would be interesting to address the origin of such a discrepancy that we observe with BNW results. But we also need finite spacing to go to higher temperatures, because as you can see, we arrived at a maximum of the order of 600 MeV, but of course we would like to arrive up to the GeV scale or maybe also above. I'm not saying that the solution is around the corner, because I don't think that will be true, but surely there are several proposals that are under, current studied. So, I think that there are reasons to be optimistic. For instance, there is the proposal by Hasenbusch of the parallel tempering of boundary conditions, on which I have worked a lot on these two papers here. There is the machine learning equivariant flows proposal. There is the density of stage proposal with the parallel tempering on the coupling. So, probably some news will be found in next years. Okay, I'm done. Thank you.
Thanks so much, Claudio, for a very, very interesting presentation. Questions? Yes, please.
Yeah, so maybe comment / question. Is it conceivable? Well, I guess as a matter of principle, it is conceivable, but is there any hope to put such a pseudoscalar field in the simulation? And of course, you would have to presumably take an axion decay constant, which is of the same scale as everything else on the lattice, and then basically measure the mass of this particle directly, rather than going through this expansion.
So you mean to put directly the axion in the lattice simulations and
just as a field, just as you gauge fields? Yeah.
Mm-hmm. I don't know, actually. No, actually, I don't know the answer to this question.
I guess it might also depend on the particular realization, because if you just put an axion with a certain mass and FF tilde there, okay, but if you give the axion a mass to start with, then I guess you get a shift. But if the axion is massless to start with, then of course, in a fixed topological sector, you generate a potential which is bottomless. So one would have to put in some information on the axion potential, that it's living on a circle and have its decay constant in there.
The axion potential in the framework that I explained to you is the result of an integration of the QCD sector. So there is already an integration of the topological sectors.
Right, but I mean a potential in the sense, let's assume you have this topological freezing and you have a dynamical axion field there. Yeah. Okay, and so if all I'm putting on the lattice is, so let's say I'm in the sector Q=1, and I put a massless particle coupling to FF tilde, then I would have a bottomless potential, because I can always minimize the action by changing the value of the axion field. So something else has to be going on. I guess in the underlying model, the axion lives on a circle, as given by radius parameterized by the axion decay constant, and that would inhibit the axion going all the way down the bottomless pit. But then the next question I would have with these topological sectors in finite volumes is, so if you do this, you have topological freezing, then I think it would look to me in such a model that in the sector where I have Q=0 for an axion that's living on a circle, the mass would remain 0. If the chiral susceptibility is dominated by these discrete topological sectors, of course, you will also have local fluctuations in the chiral susceptibility, which may also influence the axion mass. And then in the sector with Q=1, I would have a different mass and so on. So spectrally, I would have a superposition of these different particles. So yeah.
No, sorry. Again, I mean, my point of view. I mean, the usual point of view in which I think is that, I mean, the mass of the axion is the result of an averaging of the QCD sector. So you cannot speak about the axion mass without computing the susceptibility, which is, I mean, which is an averaging of Q squared. So I'm sorry, but I don't know the answer to your question.
Yeah, right. But I mean. Of course, I'm not inventing this, but I would believe that if my volume is not very large and I have these different topological sectors and I have some dominance, so the current susceptibility is somehow dominated even locally by these frozen topological sectors, that in these different topological sectors by this procedure, I mean, I guess it's hypothetical, I don't know how realistic it is to realize it, one would see different axion masses in each sector. Yeah. And then one would need to explain how, when one does the superposition, one ends up with a single particle with a certain pole. Yeah.
Again, I think it's. I think what you see is large finite size effects, and then it's always the same discussion somehow. So you would have large finite size effects, and then the question is, do you either sum all the sectors in fixed volume and infinite volume limit, or the other way around? I don't think that in that way one can resolve the. I think that so. There are calculations at fixed topology in QCD done, for example, for the susceptibility, even on a lattice. And what you observe if you do the calculation of fixed topology, maybe you can confirm, is that you have large finite size effects. And so the question is really, do you now do sum of all topology in fixed volume and then do the infinite volume limit, or the other way around? And I don't, the calculation is done in finite volume on the lattice. So it's hard to resolve that question, I think, in this way.
Yeah, but I think if this were possible, it would, I know that it's possible, yeah. Mm-hmm. But I think the physical answer of the mass of the pseudoscalar would be obtained on a fixed topological sector, which may have a continuum limit, and a large volume. But I agree realistically with that.
No, I don't understand. Yeah, I mean, so on this first principle simulation that you want to do, I think you would like to measure directly the axion, the action. I mean, you take LQCD in the minimal coupling into the axion, and so you would like to directly simulate that without extracting the axion potential. But I would think that would have a sign problem, because it would be more complicated than doing QCD with a theta vacuum. So it would be an upgrade of simulating directly with the theta term, because it would have the theta term plus the scalar coupled. So I think, I don't know, of course it would be very good. Yeah, that would be ideal in a sense. So we would generate this potential from the simulation, but I think sign problem will come in. And now the other
that's
thing,
essentially the same problem of simulating the QCD with a real theta term.
With a real theta term, yes, I think so. And the other thing, why you think the axion mass should be different in the different topological sectors? So do you know for sure? Because the fluctuations may be the same. No.
I mean, so if I would say simply if the current susceptibility is dominated by, and I mean, Claudio was mentioning in this talk, so in the topological sector 0, you have current susceptibility 0. And then in the topological sector 1, you have topological susceptibility 1 square. In 2, you have 2 square, and so on. And in each of these sectors, a large chunk of the contribution to the axion mass would come from these terms. And so I think I would see then in each sector different axion masses to some extent. And I think this would go away in the first principle simulation if I take a large volume limit.
But I mean, if you integrate suppose that you take a fixed sector simulation and you integrate just the 2-point correlator of the topological charge density, I don't think that you'll see 0, even though you are in the 0 sector. It's a sort of the problem that I showed, the paper that I showed you on Monday.
Yeah, I mean, the
The slab
pseudoscaler
method.
should see the local fluctuations. Yeah, so you can locally
Yeah.
measure topological susceptibility, and from there one would expect that the mass doesn't remain 0. Yeah. But I mean, there's also these contributions from the discrete charge, and yeah, this might be like some systematic finite volume contamination here. Yeah.
Are there more questions or comments from home, from Zoom? Well, if not, let's thank Claudio again.